As I mentioned in the last video, we're going to start to prove statements that involve even and odd integers. So in order to actually do this, we first need definitions of even and odd integers. So I'll give you these definitions. We'll introduce a property of integers that we'll be able to use for proofs. And finally, we'll prove result 3.16. So first off, definition of even and odd. So what does it mean for an integer to be even? We mentioned this in one of the classes. We had this debate of whether or not 0 was even or odd. And someone in class mentioned that an even integer is one that is a multiple of 2. And so 0 is even. In particular, 0 is even. So how we give that definition is we say that an integer is even if n is equal to 2a for some integer a. That is, n is a multiple of 2. So if we know an integer is even, that means we can find this integer a such that n is equal to 2a. And if we want to prove that an integer is even, all we have to do is find this integer a and write our integer n as twice that number. That would prove that an integer is even. Similarly, an integer is odd if it's one more than an even integer. We'll accept this as our definition of an odd integer. So, right, an integer n is odd if n is 2a plus 1 for some integer a. So again, if we know our integer is odd, then we can write it as 2a plus 1 for some a. And if we want to prove an integer n is odd, it's enough to write it as twice some integer plus 1. Okay, we're going to get to this result, but first we need to discuss this property of integers. That is, it's sort of very obvious, and so we're just going to accept it as fact, just like we accepted that property of real numbers as fact without a proof. You'll just have to trust me that it is really true. And this property of integers is that if I have an integer a, if a is an integer, then so is the negative of it. And if a and b are integers, then their sum is also an integer, and their product is also an integer, right? It seems obvious, but we'll just state this property so that we can use it in our proofs. All right, on to the result. So let's again talk strategy. What are our assumptions? What are we trying to show? So we're going to assume n is odd. And we're going to show that 5n plus 3 is odd. So assuming n is odd, that means I'll be able to write it as twice another integer plus 1. So what this means is that there exists an integer a such that n is equal to 2a plus 1. That's our definition of an odd number. We're going to use this fact then to show that 5n plus 3 is odd. So I'll want to write 5n plus 3. I'll want to write it as twice some other integer b plus 1. Not necessarily the same a, right? Just some integer b, twice that plus 1. So that's my goal. Notice that by assumption I'll have n equal to 2a plus 1, and I can actually plug this in. And then I'll just have to manipulate this a bit. I'll have to use some algebra to show that I can write it as twice some other integer plus 1. So what this b is going to come out in the proof once I plug this 2a plus 1 in. That is, this b is going to depend on a. It's not going to be equal to a, but it is going to depend on a. So let's actually prove this thing. So I'll say let n be odd. Then, by definition, n is equal to 2a plus 1 for some a in the integers. And like I said, now that we have now that we know what n is in terms of this, right, we have some expression for n, now we can plug it into 5n plus 3. So 5n plus 3 is equal to 5 times 2a plus 1 plus 3. And now I'm just going to do some algebra, simplify this. This is 10a plus 5 plus 8. So that's 10a plus 8. Wait a second. right. No, this result is false as stated. So careful me. I actually want to show that 5n plus 3 is even. So I don't want to show that it's equal to 2b plus 1. I want to show that it's equal to 2b. So I'm not going to go back and re-record this video even though I made that mistake. Why? Certainly it would be better for my ego to just go back and re-record this. Because then you wouldn't have seen me make this mistake. But I think it's important that you see when you make a mistake like that, how did I recognize that it was a mistake? Well, I recognized that I had this written as 10a plus 8, that this is actually going to turn out to be even, and then my statement wouldn't have been true. So that's how I recognized that I made a mistake. And what did I do when I made that mistake? I went back and I changed those parts that were incorrect, right? I restated the result, and I fixed what I wanted to show. I fixed that. So now I'm ready to keep going. So 5n plus 3 is equal to 5 times 2a plus 1 plus 3. That's 10a plus 8. And again, my goal is to write this as twice some other integer. That is, I want to try and factor a 2 out of it. So this is the same thing. Notice that, right, 10 is a multiple of 2, 8's a multiple of 2. So this is 2 times 5a plus 4. Now my claim is that 5a plus 4, that this makes 5n plus 3 to be an even integer. What I need to do, I need to demonstrate that 5a plus 4 is an integer. Since a is an integer, I'll say clearly, right, we're using that property of integers here. 5a plus 4 is an integer. So 5n plus 3 is even. I've written it as twice some other integer. I've demonstrated that this really is an integer using that property of integers. And so I know now that 5n plus 3 must be even. That's my proof. I'm done. Let's do one more like this. I also want to prove result, I think 3.18 is the one I picked out. So result 3.18. This says that if n is an even integer, then so is 5n cubed. So again, let's talk strategy. My assumption is going to be that n is even, and so n must be equal to 2k for some integer k, right? That's what it means to be even. And then I'm going to show that 5n cubed is also even. So I'm going to write it as twice some integer b, twice some other integer. 5n cubed equals twice some other integer. I'll call it L. So I want to show this and assume this. All right, so let's prove it. You'll notice I'll be able to use the same strategy I did the last time, right? This is what a direct proof is. I write my assumption down, draw a conclusion, and then I'll be able to plug this into 5n cubed and be able to write that as twice some other integer. So let's prove this. Now, oftentimes, right, you know, technically, or at least what I've shown you so far, my first statement is always assume that n is even. But oftentimes when we're proving something, that assumption is so obvious that we know, the reader knows you're going to assume n is even, and so we don't even say that. We just say, since n is even, n equals 2k for some integer k. Now I'm going to take this n equals 2k and I'm going to plug it in for n here and hopefully be able to write it as twice some other integer. Then 5n cubed is equal to 5 times, now n, now that I have a handle on n, I have some leverage here. N is equal to 2k and n cubed, so 2k cubed. And now I'll do some algebra again. So 2 cubed is 8. So this is 5 times 8. This is 40k cubed. right? 2k cubed is 8k cubed. And so I get 40k cubed. And again, I want to write this as twice some other integer. So this is equal to 2 times 20k cubed. And then I'll say, since k is an integer, 20k cubed is an integer. So 5n cubed, which is 2 times 20k cubed, is even. And that's the proof. All right. I'm hoping this is starting to seem kind of straightforward on how to prove a statement like this. You'll practice this in your homework. And we'll move on now to a little bit away from even and odd integers and start talking about rational numbers. So we'll see that in the next video.